In this video, I'll explain the mathematical analysis of the randomized linear time selection algorithm that we studied in the previous video. Specifically, I'm going to prove to you the following guarantee for that algorithm. For every single input array of length n, the running time of this randomized selection algorithm, on average, will be linear. Pretty amazing if you think about it, because that's barely more than the time it takes just to read the input. And in particular, this linear time algorithm is even faster than sorting. So this shows that selection is a fundamentally easier problem than sorting. You don't need to reduce to sorting. You can solve it directly in big O of n time. I want to reiterate the same points I made about quicksort. The guarantee is the same. It is a general purpose subroutine. We make no assumptions about data. This theorem holds no matter what the input array is. The expectation, the average that's in the theorem statement, is only over the coin flips made by the algorithm, made inside its code of our own devising. Before we plunge into the analysis, let me just make sure you remember what the algorithm is. So it's like quicksort. We partition around a pivot, except we only recurse once, not twice. So we're given an array with some length n. We're looking for the ith order statistic, the ith smallest element. The base case is obvious. If you're not in the base case, you choose a pivot p uniformly at random from the input array, just like we did in quicksort. We partition around the pivot, just like we did in quicksort. That splits the array into a first part, those elements less than the pivot, and the second part, those elements which are bigger than the pivot. Now we have a couple cases. The case which is very unlikely, so we don't really worry about it, is if we're lucky enough to guess the pivot as the ith order statistic, what we're looking for. That's when the new position j of the pivot element happens to equal I, what we're looking for. Then, of course, we just return it. That was exactly what we wanted. In the general case, the pivot is going to be in a position j which is either bigger than what we're looking for, I, that's when the pivot is too big, or j, its position will be less than the order statistic I that we're looking for. That's when the pivot is too small. So if the pivot's too big, if j is bigger than I, then we know that what we're looking for is on the left-hand side amongst the elements less than the pivot, so that's where we recurse. We've thrown out both the pivot and everything to the right of it. That leaves us with an array of j minus 1 elements, and we're still looking for the ith smallest among these j minus 1 smallest elements. And in the final case, this is what we went through in the quiz in the last video, is if we choose a pivot who's smaller than what we're looking for, that's when j is less than I. Then it means we're safe to throw out the pivot and everything less than it. We're safe recursing on the second part, those elements bigger than the pivot. Having thrown out the j smallest elements, we're recursing on an element of length n minus j, and we're looking for the I minus j smallest element in those that remain, having already thrown out the j smallest from the input array. So that's randomized selection. Let's discuss why it's linear time on average. The first thought that you might have, and this would be a good thought, would be that we should proceed exactly the same way that we did in quicksort. You'll recall that when we analyzed quicksort, we set up these indicator random variables xij, determining whether or not a given pair of elements got compared at any point in the algorithm. And then we just realized the sum of the comparisons is just the sum over all of these xij's. We applied linearity of expectation, and it boiled down to just figuring out the probability that a given pair of elements gets compared. You can analyze this randomized selection algorithm in exactly the same way, and it does give you a linear time bound on average, but it's a little messy. It winds up being not quite as clean as in the quicksort analysis. Moreover, because of the special structure of the selection problem, we can proceed in an even more slick way here than the way we did with quicksort. So again, we'll have some constituent random variables. We'll again apply linearity of expectation, but the definition of those random variables is going to be a little bit different than it was in quicksort. So first, a preliminary observation, which is that the workhorse for this randomized selection procedure is exactly the same as it was in quicksort. Namely, it's the partition subroutine. Essentially, all of the work that gets done outside of the recursive calls just partitions the input array around some pivot element. As we discussed in detail in a separate video, that takes linear time. So usually when we say something's linear time, we just use big O notation. I'm going to go ahead and explicitly use a constant c here for the operations outside the recursive call. That'll make it clear that I'm not hiding anything up my sleeves when we do the rest of the analysis. Now what I want to do on this slide is introduce some vocabulary, some notation, which will allow us to cleanly track the progress of this recursive selection algorithm. And by progress, I mean the length of the array on which it's currently operating. Remember, we're hoping for a big win over quicksort, because here we do only one recursive call, not two. We don't have to recurse on both sides of the pivot, just on one of them. So it stands to reason that we can think about the algorithm as making more and more progress as its single recursive call is operating on arrays of smaller and smaller length. So the notion that will be important for this proof is that of a phase. This quantifies quantifies how much progress we've made so far, with higher numbered phases corresponding to more and more progress. We'll say that the rselect algorithm at some midpoint of its execution is in the middle of phase J if the array size that the current recursive call is working on has length between 3/4 raised to the j times n and the smaller number 3/4 raised to the j plus 1 times n. For example, think about the case where j equals 0. That says phase 0 recursive calls operate on arrays with size between n, that's the length of the original input array, and 75% of n. So certainly the outermost recursive call is going to be in phase 0 because the input array has size n. And then, depending on the choice of the pivot, you may or may not get out of phase 0 in the next recursive call. If you choose a good pivot and you wind up recursing on something that has at most 75% of the original elements, you will no longer be in phase 0. If you recurse on something that has more than 75% of what you started with of the input array, then you're still going to be in phase 0 even in the second recursive call. So overall, the phase number j quantifies the number of times we've made 75% progress relative to the original input array. And the other piece of notation that's going to be important is I'm going to call xj. So for phase j, xj simply counts the number of recursive calls in which a randomized selection algorithm is in phase j. So this is going to be some integer. It could be as small as 0 if you think about it for some of the phases, or it could be larger. So why am I doing this? Why am I making these definitions of phases and of these xj's? What's the point? Well, again, remember the point was we want to be able to cleanly talk about the progress that the randomized selection algorithm makes through its recursion. And what I want to now show you is that in terms of these xj's, counting the number of iterations in each phase, we can derive a relatively simple upper bound on the number of operations that our algorithm requires. Specifically, the running time of our algorithm can be bounded above by the running time in a given phase and then summing those quantities over all of the possible phases. So we're going to start with a big sum over all the phases j. We're going to look at the number of recursive calls that we have to endure during phase j, so that's xj by definition. And then we're going to look at the work that we do outside of the recursive calls in each recursive call during phase j. Now, in a given recursive call, outside of its recursive call, we do c times m operations, where m is the length of the input array. And during phase j, we have an upper bound on the length of the input array. By definition, it's at most 3/4 raised to the j times n. So that is, we multiply the running time times this constant c. This we inherit from the partition subroutine. And then we can, for the input length, we can put an upper bound of 3/4 raised to the j times n. So just to review where all of these terms come from, this 3/4 j times n is an upper bound on the array size during phase j. This is by the definition of a phase. Then if we multiply that times c, that's the amount of work that we do on each phase j subproblem. How much work do we do in phase j overall? Well, we just take the work per subproblem, that's what's circled in yellow, and we multiply it times the number of such subproblems we have. And of course, we don't want to forget any of our subproblems, so we just make sure we sum over all of the phases j to ensure that at every point we count the work done in each of the subproblems. Okay, so that's the upshot of this slide. We can upper bound the running time of our randomized algorithm very simply in terms of phases and the xj's, the number of subproblems that we have to endure during phase j. So this upper bound on our running time is important enough to give some notation. We'll call this star. This will be the starting point of our final derivation when we complete the proof of this theorem. Now don't forget, we're analyzing a randomized algorithm. So therefore, the left-hand side of this inequality, the running time of rselect, that's a random variable. So that's a different number depending on the outcome of the random coin flips of the algorithm. Depending on the random pivots chosen, you'll get different running times. Similarly, the right-hand side of this inequality is also a random variable. That's because the xj's are random variables. The number of subproblems in phase j depends on which pivots get chosen. So to analyze, what we care about is the expectations of these quantities, their average values. So we're going to start modestly, and as usual, this will extend our modest accomplishments to much more impressive ones using linearity of expectation. But our first modest goal is just to understand the average value of an xj, the expected value of xj. We're going to do that in two steps. On the next slide, I'm going to argue that to analyze the expectation of xj, it's sufficient to understand the expectation of a very simple coin flipping experiment. Then we'll analyze that coin flipping experiment. Then we'll have the dominoes all set up in a row. And on the final slide, we'll knock them down and finish the proof. So let's try to understand the average number of recursive calls we expect to see in a given phase. So again, just so we don't forget, xj is defined as the number of recursive calls during phase j, where a recursive call is in phase j if and only if the current subarray length lies between 3/4 raised to the j plus 1 times n, and then the larger number of 3/4 raised to the j times n. So again, for example, phase 0 is just the recursive calls in which the array length is between 75% of the original elements and 100% of the original elements. So what I want to do next is point out that a very simple sufficient condition guarantees that we'll proceed from a given phase on to the next phase. So it's a condition guaranteeing termination of the current phase. And it's an event that we've discussed in previous videos, namely that the pivot that we choose gives a reasonably balanced split, 25-75 or better. So recall how partitioning works. We choose a pivot P. It winds up wherever it winds up, and the stuff to the left of it's less than P. The stuff to the right of it's bigger than P. So 25-75 split or better, what I mean is that each of these, the first part and the second part has at most 75% of the elements in the input array. Both have at least 25% and at most 75%. And the key point is that if we wind up choosing a pivot that gives us a split that's at least this good, the current phase must end. Why must the current phase end? Well, if we get a 25-75 split or better, then no matter which case we wind up in the algorithm, we're guaranteed to recurse on a subproblem that has at most 75% of what we started with. That guarantees that whatever phase we're in now, we're going to be in an even bigger phase when we recurse. Now I want you to remember something that we talked about before, which is that you've got a decent chance when you pick a random pivot of getting something that gives you a 25-75 split or better. In fact, the probability is 50%. Right? If you have an array that has the integers from 1 to 100 inclusive, anything from 26 to 75 will do the trick. That'll ensure that at least the first 25 elements are excluded from the rightmost call, and at least the rightmost 25 elements are excluded from the left recursive call. So this is why we can reduce our analysis of the number of recursive calls during a given phase to a simple experiment involving flipping coins. Specifically, the expected number of recursive calls that we are going to see in a given phase j is no more than the expected number of coin flips in the following experiment. Okay, so you have a fair coin, 50% heads, 50% tails. You commit to flipping it until you see a head. And the question is, how many coin flips does it take up to and including the first head that you see? Okay, so at minimum, it's going to be one coin flip. If you get a head the first time, it's 1. If you get a tails, then a head, then it's 2. If it's tails, tails, heads, it's 3, and so on. And you always stop when you get that first head. So what's the correspondence? Well, think of heads as being you're in phase J, and if you get a good pivot that gives you a 25-75 split, call that heads, and it guarantees that you exit this phase J, just like it guarantees that you get to terminate the coin flipping experiment. Now, if you get a pivot which doesn't give you a 25-75 split, you may or may not pass to a higher phase J, but in the worst case, you don't. You stick in phase J if you get a bad split, and that's like getting a tails in the coin flipping experiment, and you have to try again. This correspondence gives us a very elementary way to think about the progress that a randomized selection algorithm is making. So there's one recursive call at every step in our algorithm, and each time we either choose a good pivot or a bad pivot. Both could happen, 50-50 probability. Good pivot means we get a 75-25 split or better. Bad pivot means, by definition, we get a split worse than 25-75. So what have we accomplished? We've reduced the task of upper bounding the expected number of recursive calls in a phase J to understanding the expected number of times you have to flip a fair coin before you get one heads. So on the next slide, we'll give you the classical and precise answer to this coin flipping experiment. So let me use capital N to denote the random variable, which we were just talking about, the number of coin flips you need to do before you see the first heads. And it's not very important, but you should know that these random variables have their own name. This would be a geometric random variable with parameter 1/2. So you can use a few different methods to compute the expected value of a geometric random variable such as this, and brute force using the definition of expectation works fine as long as you know how to manipulate infinite sums. But for the sake of variety, let me give you a very sneaky proof of what its expectation is. So the sneaky approach is to write the expected value of this random variable in terms of itself, and then solve for the unknown, solve for the expectation. So let's think about it. So how many coin flips do you need? Well, for sure, you're going to need one. That's the best case scenario. And now two things could happen. Either you get heads, and that happens with 30% probability, you stop. Or you get tails, that happens with 50% probability. And now you start all over again. Again, you just flip coins until you get the first heads. On average, how many times does that take? Well, by the definition of capital N, you expect the expectation of n coin flips in the case where you get tails and you have to start all over. So this 1 represents the first coin flip. The 1/2 is the probability that you can't stop, that you have to start all over, probability of tails. And then, because it's a memoryless process, because when you start anew on the second coin flip having gotten the tails, it's as if you're back at time 1 all over again. So now we have a trivial equation in terms of the unknown expected value of n, and the unique solution, the unique value that the expected value of capital N could have in light of this equation is 2. So on average, if you flip a fair coin and stop and you get heads, you're going to see 2 coin flips on average. To make sure you haven't sort of lost the forest for the trees, let me remind you why we were talking about this coin flipping analysis in the first place. So recall on the previous slide, we showed that xj, and remember xj is the number of recursive calls you expect to see in a given phase j, and we argued that the number of recursive calls you're going to see is bounded above by the expected number of coin flips until it heads. So this exact calculation of 2 for the coin flips gives us an upper bound of 2 for the number of recursive calls on average in any given phase j. So now we got all our ducks lined up in a row. Let's wrap up the proof on this final slide. So inherited from part 1 of the proof, we have an upper bound on the expected running time of the R-select algorithm. This is what we were calling star on the first proof slide. In star, it looked a little messy, but we had the sum over the phases j, but we had two things that were independent of j, the constant c and the original input linked n. So let me just yank the c and the n out front. And then we have this residual sum over the phases j of 3/4 raised to the j. Remember, that comes from our upper bound on the subproblem size during phase j. And then, of course, we have to keep track of how many phase j subproblems we got to solve. That, by definition, is xj. Now, star was written as a inequality in terms of the random variables. Now we're going to go ahead and take the expectations. And again, I've said this over and over, but don't forget, where does the expectation come from? This is over the random pivot choices that our code makes. So the expected running time of the algorithms is mostly the expectation of this starred quantity. So like I said earlier, pretty much every time we're going to do any analysis of a randomized process, we're going to wind up using linearity of expectation at some point. Here's where we do it. Linearity of expectation says the expectation of a sum is just the sum of the expectations. So we yank the c and the n outside of the expectation. We yank this sum over phases outside of the expectation. We yank this 3/4 raised to the j outside of the expectation, and then we just have the expected value of xj, the average number of recursive calls we expect to see in phase j. Now, in the previous two slides, we figured out an upper bound on how many recursive calls we expect to see in each phase. So first, by the coin flip analysis, by the reduction to the coin flip analysis, this is the most expected number of coin flips n, which on the previous slide we argued was exactly 2. So bringing that 2 out in front of the sum, that no longer depends on j. So we get a most 2cn times the sum over phases j of 3/4 raised to the j. Now, this kind of sum we have seen previously in the course. It came up when we were analyzing the master method, and we summed up our running time upper bounds over the levels of our recursion tree. And if we're not in case 1, if we were in case 2 or 3, we had geometric sums that were non-trivial, that required a certain formula to calculate. So let me remind you of that formula here, when 3/4 is the number being powered up to the j. So this has value at most 1 over 1 minus the number that's getting powered. So in this case, it's 3/4. So 1 minus 3/4 is a quarter. You take the reciprocal, you get 4. And the upshot is that the expected number of operations that this randomized selection algorithm uses to find the ith ordered statistic in a given input array is 8 times c times n, where c is the hidden constant in the linear running time of partition. And so that completes the proof. The input array was arbitrary. We showed the expected running time over the random choices of the algorithm is linear in n. That is only a constant factor larger than what is required to read the input. Pretty amazing.